velocity. Now let's have a look at a velocity time graph. Very similarly, we're going to do a very similar kind of thing. Okay, this graph is from the previous video on interpreting velocity time graphs and distance time graphs, but it's a little bit small for us to work with, so let's zoom in. Okay, again, the first thing I'll do is write down the formula. Change in velocity divided by time taken. So this time I'm going to select the change in velocity over this little purple section you can see here, and I'm going to divide it by the time it took for that change in velocity to happen. Very similar to what happened previously with the distance time graph. And the time it took for this change in velocity is represented by this blue line. Now again, let's just count the boxes, one box for that, and I'm going to just pretend now that these boxes for velocity are equal to 1 meter per second each, so that's 1 meter per second, 2 meters per second, 3 meters per second, so on, and the time is going to be 1 second for each box as well, just to keep it simple with our calculations. Okay, so now I need to get the time, a figure for the time. So there's 1, 2, 3, let's just count the boxes, 3, 4, 5, 6, 7, 9, 8.6. So I reckon there are 8.6 squares between here and here. Okay, so I can stick the numbers into a calculator and get my answer, but if you were paying attention to the previous section, this answer is not going to get me many marks in an exam. So let's go to the correct number of significant figures. The greatest accuracy I could read off the graph was to one significant figure, so my answer can only be to one significant figure. So that is, the number there now is correct. And secondly, I now have some units, and it's vital to notice that the units for acceleration are meters per second squared, not meters per second like with velocity, it's meters per second squared. Acceleration means how velocity changes with time, and velocity is in meters per second, so it's like meters per second divided by meters per second, which if you mess around with the maths, you get to meters per second squared. Okay, so that was acceleration from velocity time graphs. Now, how we calculate distance covered from velocity time graphs. Again, this is from another graph from the previous video. We'll zoom in a bit so it's clearer and easier to see. This time it's telling me the velocity and how it changes with time. Okay, so I wanted to work out the distance. So I can take the velocity equation, rearrange it by multiplying both sides by time taken. So the velocity here has been multiplied by time taken, and change in distance has been multiplied by time taken, apart from when you multiply the change in distance by time taken, the time taken on this side will cancel out with itself and you're left with change in distance over 1, which is the same as change in distance. So I've just done a basic rearrangement of this equation and just tidied it up and put it the right way around here. Well, the conventional way around. Okay, so now let's read off the velocity. It's the height here times the time, which I'm just going to choose at random. So I'm going to choose to find out how far this object would travel in 1, 2, 3, 4, 6, 7 seconds. Okay, so my velocity, you can read off now without me putting the blocks in, is just 1, and it was 7 units of time. Now you could work out the distance for any number of units of time as long as the graph goes on, and then work out the distance covered for any amount of time. But I'm just choosing a random one here, just for the purpose of the presentation. Okay, so again we stick the numbers into a calculator. I'm sure you wouldn't need to, but you get an answer. And I'm sure you can spot the mistake with this answer now. Right, we didn't have any units. It was the correct number of significant figures, but we didn't have any units. So the correct answer would be 7 meters, as we were working out the distance travelled. Distance is in meters. Okay, and conventionally in physics, the conventional measure of distance is meters. Okay, let's have another look at another example of how to calculate distance from a velocity time graph. This time we're looking at something which is accelerating uniformly. Zoom in on the graph a bit, make it easy to interpret. And this time I want to calculate the distance travelled by the object in the graph, but the entire graph. I want to know how far has the object travelled in the entire amount of time that's represented on this graph. So again, use the formula we derived earlier. But this time I hit a stumbling block. I want to use the velocity, but which velocity do I use? Velocity here, which is 0, or velocity here, which is 2.3, or wherever, right? Well, if I use the average velocity, then I should be able to still calculate the distance travelled. So I have to work out, how do I work out the average velocity? Well, the average velocity will be the maximum velocity halved. So here, this purple line indicates the maximum velocity, and if I multiply that by a half, or divide it by 2, it's going to give me the average velocity. So I've got the one term now, I need to get time. So that's the time taken for this event, this velocity to be achieved. And as you can read from the graph, the time is all these squares here. So we need to count them all, which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22, I made a mistake there. Okay, so here we have another example of calculating distance covered with a velocity time graph. This time it's with a uniformly accelerating object. Let's just zoom in on that graph and make it a bit bigger. And I want to now calculate the distance traveled by the object, but on the distance covered by the object on the entire graph, so for the entire amount of time that's displayed on this graph. So the first thing I need to do is write down my equation. Distance is equal to velocity times time, but I hit a stumbling block because what velocity should I use? The velocity here is 0, the velocity here is 2.3, and there's a whole load of velocities in between. So in order to solve this, I shall use the average velocity. How will I calculate the average velocity? If I take the maximum velocity and halve it, that will give me the average velocity. So here the purple arrow line represents the maximum velocity. Okay, and if I multiply it by a half, I'll get the average velocity. So 2.3 is the reading there, and times by a half, that's this term sorted. So my average velocity I've found. Now I just need to find the time it took for this change to take place from 0 meters per second squared to, or meters per second, sorry, to 2.3 meters per second. And that took, as you can read from the graph, it took 22 seconds for the object to go from 0 to 2.3. So now I just stick these numbers into a calculator and I get this answer. And I'm sure you know by now this answer can be improved or isn't really very good because I haven't got the units. So this is my final answer with units to the correct number of significant figures. Okay, so to summarize for velocity time graphs, calculating the area under the line of the graph will give you the distance covered, and you can calculate the total distance covered for an object by adding up the areas of different sections of the graph. So for this object, you just calculate the area of the rectangle and the triangle. The area of the rectangle would just be the base times the height, and the area of this triangle would just be the base times the height times by a half, and then you could just add them together as shown in this formula here. And that would give you the total distance covered. Right, so by now you should be able to calculate the velocity from a distance time graph, which was just the gradient of the graph, or the rise divided by the run, which would be the change in velocity divided by the time taken. Gradient is just a mathematical term for the height of a graph divided by the run of the graph, or yeah, anyway. Again, acceleration is calculated from the gradient of a velocity time graph, and you can calculate the distance covered from a velocity time graph by looking at the area underneath it. Thank you very much. This is the end. Again, Khan Academy is my inspiration for these videos. Search for him on YouTube. He's the man.